Okay, guys. Let's have a look at these questions then together. So for each of the following scientists, describe his invention, the type of energy the inventor was able to produce, and how it was produced. Okay, Oersted, what did he produce? Or what did he do? Seebeck.
How was Seebeck?
Was the thermocouple.
He put a compass in the middle of a wire.
Right. Okay, so he produced a magnetic effect from electricity. Okay, he showed that electricity can have magnetic effects. Okay, Faraday was the one who did the opposite, and Seebeck is the one who did the thermocouple. So there's the first three, just like that. Okay, so what did Faraday produce? Faraday produced electricity from magnetism. Seebeck produced electricity and magnetism from heat, okay, or from thermal energy. What did Edison do?
DC.
Hmm?
DC current.
No. I mean, he had some part to play in that, but the big thing for Edison was the light bulb. Yeah. Okay. He took electrical energy and turned it into thermal and light. Yeah, because I mean it's an incandescent light bulb. That means to glow because of being really hot. Okay. And then Volta. Yeah, he made the first battery, so electrical energy from chemical energy. Okay, for each of the inventions identified in question 2, state a practical use of the invention today. Oersted, electromagnet, okay, electromagnetic transmitters, okay, anything like that that has to do with converting electricity to a magnetic effect of some kind could be credited to Oersted. Faraday, okay, we use that for generators, okay, generating alternating current. Seebeck, thermocouples are used in circuit breakers, okay, and regenerative braking systems. Edison, well, we're kind of phasing out Edison's light bulb because, well, it takes 60 watts to do the same. Sorry, what's that?
I said it's just not efficient.
It's not efficient. Yeah, it takes 60 watts to do the same job as a 5-watt LED or even a 4-watt LED. So, yeah, that's kind of a no-brainer. Yes, we still use incandescent bulbs in some applications because LEDs would melt, okay, under high temperatures. But we are obviously working on ways to insulate them because incandescent is not very efficient. Now, unless you leave your oven light on, we're not talking about a huge draw. Oh, wait a minute, my kids leave that on all the time. Yeah, okay, but it's not a huge draw if you remember to turn it off. Okay, I swear if the fridge light didn't turn off on its own, he'd leave that one on. It goes off, by the way, when you close the door.
Yep.
Okay. All right, and then for Volta, well, we still use batteries. Okay, the pile alkaline battery, okay, is still something that we put in lots and lots of devices today. Okay, number 4, what is the difference between nuclear fusion and nuclear fission?
Splitting the atom versus smushing the atom.
Right, splitting the atom versus smushing the atom. Yes, okay, so splitting the atom is fission, okay, smushing the atom, okay, is fusion. That is where we crush atoms together, okay, and get the energy that way, okay. We were actually looking at in my physics class yesterday what the largest nuclear weapon ever detonated by man was, okay, and it was Tsar Bomba, which is a Russian bomb, 57 megatons. Okay, that means if you could, like in a Minecraft style way, pile 57 million tons of dynamite all in one place and blow it up at the same time, that would be like that bomb. Okay, so massive, massive explosion. They had no idea it was going to be so big when they detonated it because they actually dropped it from a plane on their own soil in the test.
Disappeared the atom.
Okay, yeah, hundreds of miles away, houses were destroyed. Okay, it's crazy. So there's probably some big chunk of Siberia that's, you know, completely uninhabitable. Wait, most of Siberia is completely uninhabitable. Well, but this would be for another reason. Okay, yeah. All right. What is the modern theory of the source of energy for the sun? Nuclear fusion. Okay, the sun has immense gravity because of its immense mass, so much so that its gravity can smush hydrogen atoms together to form helium atoms in the fusion reaction. Okay. Contributions of the following people. Okay. Did we talk about Carnot? He's in there somewhere, but I don't think we talked about him. Yeah, right here. French engineer. Okay. He transformed heat into mechanical energy. Okay. He's kind of a big part of the development of like steam engines and internal combustion engines and things like that. That was his kind of contribution. Okay. We kind of skipped over him to get to Joule yesterday. Okay, and then Joseph Black, okay, he was the guy who invented the idea of that caloric fluid, because if you put something cold in something hot, the something cold gets hotter. Okay? So he discovered that in thermodynamics, energy flows from hot to cold.
Are we gonna have to remember all these names?
I'm not terribly concerned about them. Like, I would say the biggest ones would be like Joule. Joule's pretty important. Okay, know the stuff they discovered, not so much who discovered it. Okay. James Young, okay, he's like the mechanical energy guy, okay, kind of came up with that idea that those two go together, okay, linked mechanical energy to kinetic and potential energy in objects, okay, and then for Rumford, okay, he was the one who discovered that heat, okay, or that mechanical energy be converted to heat, okay, through the people boring out the cannons and taking coffee breaks, okay. All right, explain how Joule proved that heat could be produced from potential energy. So this is the falling block experiment, okay? It goes back to Newton's cradle. When you pick up that falling block and you move it up here, you do,
Potential energy.
okay, work. And you give it potential energy. You change its energy. Any change in energy is requiring work, okay? So you do work, you give it potential energy, okay? And then when you let it go, that potential energy turns into kinetic, and the kinetic can then do work on the block. Since the block can't move, the mechanical energy gets turned into heat. So it showed that potential energy could be converted into heat. It would require intermediate conversions, but it could be done. Okay, for number 12, okay, identify the major form of energy involved. Could these be like multiple choice questions? Yeah. Okay, an antacid tablet is placed in a glass of water and the tablet starts to bubble. Chemical, plop, plop, fizz, fizz. Okay, all right. B, a fluorescent dial on a wristwatch glows at night. If it's fluorescent, if it was just the one like you push the button and it glows, absolutely it would be electrical then. Okay? These are ones that if you just have them in the light and then you go into the dark, they continue to glow. It could be solar. I would say you could also just say light energy, period. Okay? But it's also kind of a chemical thing, okay? Because it's how photosynthesis works. Right? The light gets absorbed and the electrons jump from lower energy levels to higher energy levels, and then when you take them out of the light, put them in the dark, the electrons fall back down to lower levels and they release the light. So it's sort of chemical as well. Okay? All right, a downhill skier begins to ski down the slope with increasing speed. Potential converting to kinetic, or there could be one answer that would rule them all. Mechanical energy, because mechanical energy is the sum of both of those. So any one of those would be right. But if we were looking at a multiple choice question where you're supposed to pick the best answer would be mechanical, because it would encompass all of them. Okay? All right. A tingling sensation is felt on the tongue when it is touched to the terminals of a 9-volt battery. This is a generation gap kind of question. I doubt any of you have ever done this. Okay, it's electrical energy, but that's back in the day how we used to test 9-volt batteries. Now, hardly anything takes 9-volt batteries except like smoke detectors. Okay, so yeah, there's lots of things when I was a kid took 9-volt batteries. I don't know, is that one good? I don't know. Ah, yeah, that one's okay. Yeah. Okay. So it was that was how you tested them back in the day. All right, the inside of a car gets extremely warm if the car is left in the sunshine. Thermal energy, we could say solar energy as well, probably for that one. Okay. A seagull lifts a clam high above the beach. And?
Kinetic.
And? Mechanical. Yeah, okay, because I've never seen a seagull hover. Okay, birds have a great deal of difficulty like hovering unless they're a hummingbird. Okay, the structure of their wings makes it difficult for a bird to technically hover. Okay, so there's always some forward and backward kind of motion when they flap their wings. Okay, but I would say mechanical and potential, and if it's the act of lifting it, it could also be kinetic. Okay, we're not really told whether that's going higher or staying put in one place because the question's kind of vague. They'd all be okay as answers. Okay. A compass needle held over the surface of the earth points north. Magnetic. Okay. All right. Describe an appliance or machine that for its operation requires the following forms of energy. Chemical.
Battery.
Anything that needs a battery? Anything that burns fuel of any kind?
Car.
Okay, a car, a lawnmower, okay, something like that. Light energy.
Solar panel?
Anything that runs on a solar panel, yeah. Okay, and while this isn't a machine, you could say plants. Okay, they require light. Heat.
Steam
Yeah, a steam engine, a thermocouple, yeah, anything that's going to try and convert thermal energy into mechanical energy. Okay, electrical.
Cell phone.
Yeah, anything you plug into the wall. Okay, could be listed here. Okay, hair dryer, toaster, okay, whatever. And then magnetic.
Speakers.
Speakers, yeah. Okay, I don't know if anyone's ever seen how a speaker works, but on the back of the speaker is a big ring magnet. Okay, and the magnet applies force, and the speaker moves back and forth. You can see it on subwoofers best because tweeters move too fast for you to see other than a blur. Okay, but on a sub, when it's going, it does that thing. Okay, and then you can see the magnet pulling the cone back. Okay, and then letting it, kind of pushing it forward, and sort of compressing the air. Okay, if you're in a car that someone's got like 4 subs in the back, you can get a massage. Okay, you just point the subs at the back of the chair and you can go. And you can feel it against the back of the chair. All right. Because I know that guy that drives by my house. I'm sure he has like 6 subs. Does he go by your house too? The rolling rave is what I call him. Yeah.
My
Anyway.
neighborhood.
He's always playing the same song.
My neighborhood, there's just a Dodge Charger that's really loud.
Okay, so he's got the motor and the stereo.
Not the stereo, just.
Oh, just the motor? Okay. Yeah. That guy goes through my neighborhood too, but it's like a big diesel. Yeah. Okay, questions on any of those? Okay, so that's the stuff, guys, on the types of energy. That's going to be mostly multiple choice stuff. Okay, when it comes to your Unit 3 exam, it's not going to be a huge part of anything, but just knowing the types of energy. Mechanical energy, potential energy, and kinetic energy are the types we're going to talk about most in this unit. Okay, do our calculations and stuff with. All right, for those. Okay. Now, we ended off yesterday and we were talking about Young's stuff and Black's stuff about thermodynamics. Okay? Now, the laws of thermodynamics are important laws that govern how things work. Yes. Okay? Govern how things work, but how they work because of how energy moves. Okay? So the laws of thermodynamics govern how energy can move, how work can be done, okay, and things like that. The first law of thermodynamics is the easiest one. It's the law of conservation of energy. Energy can't be created and it can't be destroyed. So the conservation laws, conservation of mass, conservation of energy, work pretty much the same. Okay? There is some terminology, though, that we have to understand when it comes to thermodynamics. Okay? And one of the first terms is thermodynamics. Okay? Thermo meaning energy, okay? Mostly heat. Okay? Dynamic meaning changing. So, okay, it's the relationship between work and energy, okay? The transformations that can occur and the direction that energy generally flows. That's actually the second law of thermodynamics. The second law of thermodynamics tells us that energy always flows from high to low. Okay? Typically when we're talking thermodynamics, that's hot to cold, okay? But it can also mean from a high energy, mechanical energy object to a lower mechanical energy object. Okay. So, systems. Okay? The word system comes up a lot when we're talking about energy and work and thermodynamics. So a system is a set of interconnected parts. Okay? That's a very general kind of definition, but it has to be because systems are all very different. There's a huge spectrum, okay, that systems would fit onto. All right, we could consider, you know, this classroom to be a system. Okay, it would contain all of us, the desks, the floor, the windows. Okay, and if we wanted to kind of end it with the walls of this room, everything else outside of those walls would be considered the surroundings. Okay, everyone all right with that? Now, does energy flow from the system to the surroundings, or vice versa? Okay, is it colder outside than it is in here right now?
Yeah.
Okay, so does that mean that energy would naturally try to flow to the surroundings?
Yeah.
Yes, and it does. Okay, this room is not well insulated. Okay, so energy does flow out. On hot days, energy flows in. Yeah, and this room gets warmer. Okay, I use thermodynamics to heat this room, namely you. The climate control in here is so incredibly crappy, and I'm recording that. Okay, it's so incredibly crappy that I never have to adjust the thermostat. I leave it on off. In 4 classes during the day, the presence of between 25 and 30 people in this room will cause the temperature in this room to go up between 6 and 8 degrees over the course of the day. Be thankful you have to put on a sweater in period 1. By period 4, we're just sweating away in here, okay? Because it's usually like 24, 25 degrees. Doesn't matter how cold it is outside, okay? That's how hot it gets in here, all right? So I'm saving the taxpayers money because I'm not actually using any energy to heat the room that we pay for. I'm using you. Okay? And I'm using the second law of thermodynamics. You're all 37 degrees Celsius. The air in here right now is 19.4 degrees Celsius. So energy is naturally flowing from you to the air.
So
Okay?
since you're using my energy, do I get minimum wage?
No, you don't. See, I'm providing a service to you already by teaching you. So we're exchanging services. I know that sucks for you, because I get paid for it, but you don't. Yeah. But what you're learning will maybe help you get paid for something later.
Maybe.
Yeah. Okay. So system is a set of interconnected parts, and we set the boundaries, but the boundaries are arbitrary. We can pick whatever they are. Okay? We could say that the boundaries are the wall, or we could say that the boundaries are the town, or we could say the boundaries are the desk. Okay? We can set those boundaries are completely arbitrary. Okay? All it determines is this is the system and this is the surroundings. Okay? Now, there are different kinds of systems, 3 different kinds. Okay? And they have to do with what the system can exchange with the surroundings. Okay? Obviously, energy can be exchanged. We were just talking about that. Okay? Can matter be exchanged? Yeah. Okay? I mean, there's not a perfectly airtight seal on those windows either. Okay? There's going to be some air being exchanged. There's also supposedly an air circulation system on these vents.
Supposedly.
There's a tiny little bit of air moving past my fingers. So there's some exchange of matter, okay, between this room and the surroundings, okay, the air, which is good because if there wasn't an exchange of air, we would eventually suffocate in here, okay, because we would consume all the oxygen and only be left with carbon dioxide to breathe. So air circulation is kind of important. Okay, everyone kind of follow me there? All right, so we define the systems based on what they can exchange. An open system is the simplest kind. It exchanges matter and energy with the surroundings. Most systems are open systems. Okay, both matter and energy is exchanged. Okay? If we were just looking at like you, for example, as a singular person, you would be an open system, right? You are not only exchanging energy with your surroundings because you're hotter than they are, okay? But also you're exchanging matter, Okay, you're consuming oxygen, you're releasing CO2, okay? You consume water and food, those are part of your surroundings, okay? So there's an exchange of both things in that open system, okay? A closed system cannot exchange matter, but can only exchange energy. So if you were, let's say you cooked dinner tonight and you had some leftovers and you wanted to freeze them, okay? You would put them in a sealed container, right? Clamp it shut so that it's sealed airtight, put it in the freezer. When you put it in the freezer, it exchanges energy with its surroundings. It gives them to the freezer and it gets colder, okay? Everyone kind of follow me there, right? And then as it freezes, no air goes in or out of the container. It's airtight. Nothing material can get in or out, right? Everyone okay with that? So anything that makes an airtight seal is going to be a closed system. It can still exchange energy, but it cannot exchange any matter. And then the last one. These are purely theoretical, okay? Isolated systems. One that cannot exchange matter or energy with its surroundings. So to make a perfectly isolated system would mean it would have to be energy independent, okay? That means make all of its own energy and never exchange any with the surroundings, which is theoretically impossible, okay? And it would have to be also perfectly insulated so that no energy ever escaped either. Okay? And it is beyond our technology, okay, to make something that is completely insulated so that no energy ever gets lost to the surroundings. Can we insulate things pretty well? Yeah. Okay. I mean, you know, if you got like a, you know, an insulated coffee mug, okay, like this one, okay, it can, you know, it's not an isolated system. It's insulated. It prevents the exchange of energy for a while, okay, but it's still eventually going to get cool. Right? Does that sort of make sense? It's usually at this point where somebody says, well, Mr. Quitter, isn't the International Space Station an isolated system? Absolutely not. Where does it get its energy from? The sun. It's getting energy from its surroundings. It's also not perfectly insulated. It loses heat to its surroundings as well. And people go on and off, okay? And every once in a while they have to dump the waste. Sometimes a poop comment. Okay, that's what Chris Field called it that. Okay, every once in a while they have to jettison the tank from the space toilet, okay, and it just burns up in the atmosphere. Thankfully, that's not one we want to get all the way to the ground. Yeah, so it's not an isolated system. Okay? It is taking in solar energy from its surroundings. It is not perfectly insulated, so it's losing energy to its surroundings as well. Okay, it's a closed system for sure. Okay, it's, you know, not going to allow matter in or out unless, you know, we're bringing supplies to it. Okay, but it is, you know, we want it to be airtight, obviously. Okay, everyone understand the three systems? Okay, that's something we'll need to know. That could be a quiz question. Okay, that could definitely be multiple choice kind of material, okay, on a test. Okay, also here, guys, we wrote this down yesterday. I said it was important. Okay, that is, work is a change in mechanical energy and heat is a change in thermal energy. Okay, I don't know why I put the triangle right on that dude's head. It makes him look like he's wearing a hat. Okay, but that's what I did. Okay, and then as we already said when we're talking about the laws of thermodynamics, okay, first law of thermodynamics is the law of conservation of energy. Okay, it says that energy cannot be created or destroyed. Okay, but it's also important to distinguish heat from work. Okay, work involves the movement of matter from one position to another or one location, whereas heat is the transfer of thermal energy from one location to another. Okay, and both of them can increase or decrease the energy of a system. Okay? Because a system can gain and lose energy in various forms. Okay? It can gain mechanical energy by being lifted or sped up, okay? Or it can gain thermal energy by being heated or lose it by giving off heat. Okay? So systems can gain and lose both types of energy, mechanical and thermal. Okay? That would be work and heat. Okay? So the energy of a system can be increased in two ways. We can heat it up, or we can make it go faster or higher. Okay, that would involve a change in mechanical energy. So we either do work or do heat. I know that sounds weird, but that's kind of what we have to do. Okay, we either do work or do heat. Okay, that means we add thermal energy. Okay. All right. Everybody okay with that? Okay, so energy can flow out of a system to its surroundings, okay, or work can be done by the system on the surroundings, okay, meaning it would lose energy by transferring it. Okay, work done by a system is considered negative work because the system loses the energy. From the surroundings point of view, that would be positive work because they would gain heat energy. Okay? And heat is the same. Okay? Negative heat would mean you've given off that heat, you now have less. The surroundings would have positive heat because it would be gaining it, right? Which is exactly what's going on in this room right now. Okay? Temperature in here has already gone up. Okay? What? Since this morning, 1.5 degrees since you guys came in. You're really good at heating this room. You need to pat yourself on that. You guys are really good at heat. Okay? Transferring thermal energy from one place to another. All right, so first law of thermodynamics is really just a restatement of the law of conservation of energy. The total energy, including heat in a system and its surroundings, remains constant. Okay, that is, energy can't be created and it can't be destroyed. It's another way of saying it. Okay, everybody all right with that first law? Okay, so what that means is if I add heat to the system, then it's going to either increase the heat, the thermal energy of the system, or the mechanical energy of the system, one or the other. Okay, that's saying energy can't be created and it can't be destroyed. Okay? So when I burn firewood, I'm not creating energy? No.
Just transferring it.
Yeah, I'm converting and transferring the energy, right? I'm converting it from potential chemical energy into thermal energy, which is then going to flow outwards to the surroundings. Okay, so yeah, I'm not creating it, I'm just turning it into something else. Okay. All right. Okay, how many people have heard of a perpetual motion machine?
Isn't it like that bird that like goes up and down?
No, those quit. I have one. Yeah, they don't run forever. They work on capillary action, so if it dries up or anything like that, it will eventually stop. It is using gravitational potential energy, mechanical energy to keep moving, because if it hits the water, there's like a capillary action that pulls the water out of the bulb at the end towards the head, and then if it continues to move, if it gets to one place too much, then it'll rock back the other way. So it isn't perpetual motion because it does actually eventually stop. But also because there is energy being put into it.
I saw one that was like fake, where it's like a ball like rolls down a ramp and then hits a jump back onto the ramp, but it's like metal, so the electrons push it forward more.
Right.
But it's like said that it's a perpetual motion.
Yeah, I mean, there's ways around that, but it always involves having something doing some work in the system. Okay, we can make a system that can run constantly and look like it's not using any energy, especially if we use magnetism, but even a magnetic object will eventually lose its magnetic ability. Okay, like a bar magnet's not going to be magnetic forever. Okay, and so that can start to wear. Okay, but a perpetual motion machine is supposed to be able to run forever and never stop. Okay, why is that impossible?
Because it was gonna be something, heat or
Friction or sound.
Yeah, there's no way to completely eliminate friction, okay? And even if we could, okay, even if we could make a system that would run forever, okay, what could it never do?
produce us energy.
Yeah. I could never use a perpetual motion machine to do any work. Because as soon as it does work, what is it transferring away?
Energy.
Right, and then it'll stop, because it can't put energy in. If I invented a machine that could do work and required no energy, that's magic. Because I would be breaking the first law of thermodynamics. It would have to create energy from nothing in order to do that. Okay? So a perpetual motion machine basically can't exist because the two laws of thermodynamics forbid it. You can't create energy, and energy always flows from high to low or hot to cold, so energy is naturally always going to flow away from the machine. Okay? So a perpetual motion machine is impossible to build because you can't make anything that's going to run forever without any input of energy. It's always going to have sound or heat or light or something like that that's coming out of it, and that represents energy being lost. Okay? Now, people have come up with all kinds of ideas. Okay? Like this one, this pi thing. Okay? So it's got these curved or arced kind of edges that make up the pi plate, and then these ball bearings inside. So the idea is that if it got spinning, the ball bearings would go out to the side, push this side down, but as they came up, because it's curved now the other way, the balls would roll back to the center where it would be easier to get this side up and over, and then they would roll away again, and it would power itself. Well,
But it would slow down essentially.
yeah, because what's it going to make?
Friction.
Yeah, I mean, unless you can make that pivot point in the middle completely frictionless, this thing is going to make noise and heat, and it's going to lose energy, and it's eventually going to stop. Could it run for a long time? Probably. Okay, if you could make it really efficient, but it is eventually going to stop. Okay, this is the one you were talking about with the magnet, right? You kind of cheat with a magnet a little bit because you're kind of getting free energy. Right? But that magnet was formed by, volcanic forces and, the deposition of minerals and things like that, okay, to get that magnetic ability. But yeah, it would pull these, ball bearings up the ramp, and then they would fall through the hole and go back down. But to open this door, they have to do what?
Hit it.
They have to do work. Right? They have to change the mechanical energy of the door. It's closed position to open position. I change the position of something, I'm doing mechanical work.
That would also
Okay?
have to be a real strong magnet to pull it up that.
Well, yeah, and that's the flaw with
Yeah,
it. If it's strong enough to pull the ball this way,
It's not gonna
how
fall
come
through
it
the
can
hole.
fall down and go down the ramp?
You're installing.
Well, it's lower, I mean, yes, but also gravity vertically is stronger than gravity along an incline, but, still. Right? It's still going to be somewhat attracted to the magnet, which is going to make it actually lose energy as it's
Pushing up
falling.
from the bottom.
Yeah, so, I don't know.
Yeah, if anything, it'd pull it up the bottom one too.
Yeah.
Because it's a field, not a little singly.
Exactly.
Yeah.
I mean, you can,
That
like a
would
field
work.
can have direction, right? Like if you put a bar magnet down like this, right, where you got north and south, and you sprinkle iron filings around it, the iron filings will draw a field like this, which is exactly the same as the Earth's magnetic field. Okay? It's got lines of field force that kind of go fan around three-dimensionally like this. Okay? And there's like a tube in the middle. Right? And so, yeah, this magnet here, you can kind of shape it a little bit. It's going to have an area of influence where it's stronger than other places, but still. Okay? I mean, there's ideas. People are always trying to do that. Okay? But the laws of thermodynamics forbid you being able to make one. Okay? Because, well, the second law of thermodynamics says that energy flows naturally, okay, from a hot object to a cold object, but never naturally from a cold object to a hot object. Notice the qualifying word in there. Never naturally from a cold object to a hot object. Does that mean it's possible to make it go that way?
Yep.
What two devices in your house do that?
Fridge.
Fridge?
Refrigerator.
Your refrigerator and?
Freezing.
Okay, I'm gonna count fridge and freezer in the same. Maybe you don't have one of these on your house. They're usually outside.
Oh, air conditioner.
Your air conditioner. Okay, if you have an air conditioner, okay, an air conditioner or a refrigerator work on the same principle. Your air conditioner is just a refrigerator for your whole house. Okay, that's why it's so much bigger and uses so much more energy than your refrigerator.
And somehow costs $1,300 per unit.
Well, I had to get mine replaced this summer. I would have loved to have got a $1,300 one. So if you got a better supplier, I could have known that months ago, and it would have been more useful.
Yeah.
Maybe it was too small. I don't know. The one I replaced was too small. That's why it burnt out. Okay. I'll start to rant if I'm not careful. So, second law of thermodynamics says energy naturally flows from hot to cold, but similar to active transport in cells, I can make energy go the other way as long as I put energy into it. Okay? It's like pumping water uphill. I can make energy go from cold to hot as long as I help it. Okay? And that's what your refrigerator and your air conditioner both do. Okay? Now, the other side of that is, if we're careful about what we do, we can use the second law of thermodynamics to do useful work. Energy naturally wants to go from hot to cold. If we can put something in the middle, it can harness that energy as it's going from hot to cold. It's called a heat engine. Okay? Now, theoretically, these are pretty simple. Okay? In a practical sense, they're a little bit more complex. Okay? But all I really have to have is a high temperature area and a low temperature area. And energy will naturally want to go this way. And if I put a heat engine in the middle, I can harness some of that energy as it goes through to do useful work. Okay? Everyone kind of with me on that? All right. So a heat engine, okay, when the heat in a heat engine flows from high temperature to low, the heat can be converted into mechanical energy. All right? One of the simplest ideas of that.
Cheese.
I'm trying to remember why I drew that diagram. Oh, I remember now. Okay, it'll make sense now. Okay, so this is like the first idea of a practical heat engine. Okay? They said, all right, we're going to build this boat. And on this boat, we're going to have cold water tank. And it'll be filled because we'll have this really long pipe that goes way down deep where the water is cold. And we'll have this other where it's warm. And it'll be really short because water near the surface is warmer than water deep in the ocean. Okay, from a practical sense, you can see that this boat would have some problems. Okay? But from a theoretical sense, it would work. Okay? I got hot water here, I got cold water here, and they're connected by a pipe. Okay? Well, then the warm water should go through the turbine because it wants to go to the cold water. It's called a convection current. You guys heard of that? Okay? Okay? It's hot to cold. Hot air rises, cool air descends. Okay? All fluids do that. Okay? So the warm water would try to go to the cold water, and on its way there, it would turn the turbine, which would produce thrust.
But the
Okay?
propeller's inside the boat. I think that's just
Well, no, it can't be inside the boat.
Because it needs,
And how-
That's what it
how
looks
water
like.
get
Well,
out?
I know it looks that way, but practically speaking, it couldn't be.
but that would never.
Okay? What's that?
How the hot water get out of the cold area? Isn't it trapped?
This is why the diagram.
cheese.
Okay? What's the motivation of the water to go through the turbine?
It wants to get the cheese.
Well, couldn't it just go, wouldn't this hot water already be cycling with the cold water below it?
Yeah.
And the hot
So what's the
water-
motivation to go through the turbine?
There isn't.
There isn't. Okay? That's what, like, why would the mouse go this way when it could just go that way? Right? Like, it's already in contact with it, already knows where it is. Why would it take the roundabout route to get to the cheese? Yeah, it wouldn't.
So wouldn't it just be an energy conversion, not, like, it's not the actual water that would go, just the temperature?
No, the water would flow with it.
It would?
Yeah,
Yeah.
okay. It's why, like, you get hot air rising, right? It's the energy that's going up, but it's taking the matter with it. Okay, it's doing that kind of mechanical work. Right? And we try and harness that in heating our homes. Right? It's why your furnace vents on your main floor and second floor, anything that's not the basement, are on the bottom. Right? They're on the floor because the air coming out is hot and it's going to encounter the coldest air first and start a circulation that can make that process more efficient. Okay? Even if you have hot water heating, the hot water pipes in your house where it's designed properly, okay, works because they're next to the floor. You know where the heating pipes are in this room?
Okay, it's us.
Over yonder.
In the ceiling.
That's nice.
Yeah, it makes good sense, doesn't it? It's a
No.
triumph of engineering. Yeah. See, this is the problem. When you do stuff wrong and science people see it, we're critical. Savagely
They just
critical.
It's cheap.
Okay? Yes, they do it because it's cheap. Everything is done because it's cheap.
Yeah, it's
That's
cheap.
why I would never become an astronaut.
And it's not. Oh, yeah.
Okay? I'm going to ride this rocket that contains several million parts, all built by the lowest bidder.
Yeah.
And that doesn't make me feel safe at all.
Yeah, the rocket was made as cheaply as possible.
Mhm. Yeah, no, thank you. All right, does this sort of make sense? That's a good rant though.
I just wanna say another thing, how would you get the boat into the water if it has a long?
See, that's the practical part of this. Right? You'd have to have some sort of telescoping
You'd have to
tube or
attach it.
something.
And what if there's like,
What
what if you just build it in, what if it's like an oil rig and you just like build it?
Yeah, yeah.
What if
There's
there's
lots
like-
of practical problems, engineering problems.
What if there's like
Use
a
boat
reed?
to get to the boat.
Exactly. You break it off, right?
Yeah, and I feel like the movement going forward would apply so much drag on that pipe that it'd bend it.
Yeah. It was never, actually, this was never a design that was ever going to be built. It was simply to proof of concept.
And also, one more time, that propeller is working
around
inside
the
the
cold
water.
water.
I'm sorry.
Like if a whale gets mad at the pipe, then like.
Oh yeah, there'd be a lot of water weight at the back, yes. Yeah, you'd have a buoyancy issue too.
I think it's
There'd
like
be
restricted.
hot
Like,
water
you don't
around
see
the
the
cold water.
definitely
Definitely.
look at the back.
Yeah,
There's
exactly.
definitely.
Yeah.
I don't know what
These are all good points. They're all perfectly valid. Yeah. Okay.
To go with somebody who's the house.
So many issues, yeah. All right, now, I'm going to show you an example here that I saw one day. I got to actually use it. This is a hot tub
No.
that works on only the second law of thermodynamics. Okay, so you fill up the tub with water, okay, and there's two pipes. You see there's a pipe up top and there's a pipe down below, okay? So they're connected to a water tank in this furnace, okay? So you've got an inner tube that is where the fire is, and then outside of that is all water, okay? Once you fill the tub up to here, this will always be full because it's lower than the tub, okay? So the entire water thing will be full of water. So you light the fire, okay? And the fire heats up the water. Hot water will rise. Okay, so the hot water will go out of this tube, this pipe, and go in to there, pushing cold water down and into this pipe and into the furnace. It creates its own circulation without the need of a pump, only using the fact that the second law of thermodynamics says hot has to go up and cold has to go down.
Oh, I saw it.
Okay?
Yeah.
So it naturally circulates, okay? To the point where it actually, you can feel it. When you put your hand in front of the opening to this pipe, you can actually feel water coming out of it, moving actually fairly quickly, okay, as a result. I'm not going to say this was really efficient, because I ran that thing for 3 hours, 2 bags of wood, okay, before I got the water in there hot enough to be a hot tub, okay? But I mean, look around, it was winter, so the water was pretty cold and semi-solid. I had to break the top.
I saw a dude
The
do
water?
the same thing with horse trough and copper wire. Took the copper tube, put in a cool circle thingy, and then the 2 tubes, filled the middle of the circle thingy of tube with wood and lit that sucker on fire.
Mm-hmm. Yeah, a heating
Almost
coil.
boiled him too.
Yeah, a heating coil. Yeah.
So those Jackson thing I know.
Okay, so that sort of makes sense? So it's a practical application, right? Like, this is not new technology. This is stuff that people have been using for ages and ages. This is how hot water heating works, okay? You have a
How the floor
boiler.
heaters work?
If you have underfloor heating with water, yes.
Oh, that's cool.
Yeah, you have a boiler that boils the water. Now, usually in a home, there is going to be a pump that assists the movement of that water, okay? But this doesn't require a pump at all. It just uses the fact that hot water is going to go up and cold water is going to go down. They're naturally going to create a convection current, and that convection current will circulate the water and keep it warm. Okay, just a practical application of simple thermodynamics. Okay, so heat engines. A jet engine is a heat engine. Okay? So in a heat engine, in a jet engine, you have the area where the jet fuel, the JP5, the kerosene basically, is burned. Kerosene burns really, really hot. Okay, like way hotter than gasoline. Okay? So it burns in this front area of the jet engine. Behind that fire are turbines. Okay? The air surrounding the engine is naturally quite what? Cool, or certainly colder by comparison to where the fuel is being burned. Okay, so what's that?
Especially high in the air.
Especially at altitude, yes. Okay, so what you get is all this heat taking air and sucking it in the front, okay, to feed the fire, and then rapidly trying to get out of there to the cold by the second law of thermodynamics. Well, as it goes through, what does it do to the turbine? It spins it, okay, and spins it fast, so fast that it produces thrust. Okay, way more than a propeller can ever hope to produce. But it's at its very core, it is just a heat engine, just like that silly boat. Okay, but more practical. right? A really, really ragingly hot area, okay? And then its surroundings being quite cold, okay? And that producing a flow through the engine that results in a great deal of thrust being produced, okay? And if you have a fighter jet, they have a second combustion area called an afterburner, okay? Which can produce even greater thrust, okay? As a result of essentially accelerating the air going through at an even greater rate, okay? So jet engines, just a simple application of the second law of thermodynamics.
Good flow.
Okay? Now, air conditioners and refrigerators go against the second law of thermodynamics because what they do is pump energy from the cold area to the hot area. Okay? So when I put my leftovers, because I'm terrible for this, like, oh, I gotta package these up, they're still warm, I throw them in the fridge. Okay? It makes my fridge work a lot harder than it should. Okay? But the fridge has got to take that heat, because the heat is naturally going to go out of that food and to the fridge. Okay? The fridge has to pump it out to the surroundings. How does that work? Well, there's a compressor.
Little mini AC.
How does that work, though?
How AC works.
How AC works?
Yeah, it's like,
There's some compression after
And
the
then what's the
compressor.
decompression that goes and stuff, it's like.
It's, yes.
It's little squeezy squeeze.
Kind of like that, yeah. Okay, so we've still got a couple minutes here. Let's look at this. So, in a fridge or air conditioner, oh, I don't have it on here. Oh, sorry. This is the heat engine. This is like one of the first ones. It's a thermoelectric converter. So if you have really hot water and really cold water and you connect the two sides of an electrical device with metal, okay, you can get that thing to run because this stuff will heat up and this stuff will be cold, and the heat will cause the particles in the metal to move faster and get this thing going, not fast. Like, you're not going to cool yourself off with that. Okay, how long will that work for? Till the temperatures are equal. It will constantly slow down. Okay, the greater the difference in temperature, the faster it'll spin. Okay, but eventually they'll equalize, and then nothing. All right, tomorrow, start of class, we're going to talk about heat pumps. Okay, air conditioners, refrigerators. Okay, and then there'll be some questions for you to do. Class tomorrow is going to be a bit shorter because we have that ELA thing and we have the Remembrance Day ceremony in period 3. Okay, so there's quite a few things going on tomorrow, so we'll just have time to basically do these questions today. Regular class.
That sounds like fun.
Okay, just watch the podcast.